So I have a question on Piazza. Let's get going with that. And feel free to add more. So the question was, what do we pass to the selection sorter? Will it be an object array? And the answer is yes, it will be an object array. And now here's a great question. Will it always be an integer array? So let's just pull up that homework real quick so everyone has context. So here. So this is to enhance selection sort, which we will be seeing in a minute, and so you're supposed to be doing it with a comparator. So as you'll see in a few minutes, the selection sort as it's presented in the book just sorts integers. And it does bring up a good question, like when is the last time that you had an array of integers that you wanted to have sorted? And normally what you want to have sorted is some other stuff. Like you might want to sort a bunch of web hits by relevance or some such thing. And then just sorting integers with less than isn't going to be good enough. So in general, you want to be able to sort arbitrary data. And one way of doing that is to supply a comparator that will work with arbitrary data. And so the reason that we use an array of objects here, go away, is, where is it? Now we use an array of objects is that here we want to be able to do just that, arbitrary data, and not just integers. And so we then supply a comparator that can compare any two objects. And so the answer is no. The answer to the student's question is it could be an array of anything at all. You could be given an array of strings together with a comparator that knows how to compare strings. You could be given an array of watermelon objects together with a comparator that compares them by size. So parameter number 1 is an array of objects. Parameter number 2 is a comparator. All right. Okay, someone found a cool app. That's good. I'll look later and see if there's other questions. Let me go through the lecture, and then we'll do a lab. And I made a lab that's somewhat related to the exam, so hopefully that'll dispel some of the lingering issues about the exam. So, selection sort. We're studying sorting for really a couple of reasons. One is that sorting is actually immensely useful, that lots and lots of computer time is eaten up by just sorting. There was someone who made a study some number of years ago at some big old mainframe in some business establishment, and they found like that 30% of the time or something like that on that mainframe was doing nothing but sorting. So lots of time people need to sort data. But actually, you might argue that if you ever wanted to sort, what you would do is you would call collections.sort or arrays.sort, and of course you'd be right. Those are very good sorting algorithms that you can just reuse. But the reason that people like to make people in a CS2 course study sorting is it's an easy problem to understand, and it gets into a whole bunch of different algorithmic choices. There are different ways of doing it, and they have dramatically different performance. So it's kind of a poster child of here's a problem that has lots of different solutions, some of them much, much better than others. And so I don't expect you to actually, for a living, program any sorting algorithms. That's been done years and years ago. So the mindset you should have is we're studying sorting because it's an easy way of getting at this study of algorithmic complexity. So having said that, let's get into some simple sorting algorithm, the one that's called selection sort. And so my slide here is slides are kind of weird. I'm just going to do this by hand. I don't know why these slides are messed up. Hang on. So let's say that I have a sequence of numbers 11, 13, 3, 9, 7, and I want to sort it. So here's the way to do it. You find the smallest number, and the smallest number will be, when you look through here, it'll be here. Of course, you have to look at the entire array to find that smallest number. So we're looking at the entire array starting from here and find the smallest number. So I know that number must be at the beginning. Now what I'm going to do is I'm going to swap it. So I'm going to put the 3 here, put the 11 here, and leave all the others in place. Now I have the smallest one in the front, and now I only need to look at the array here, and I do it again. Now actually, through the power of recursion, I'm now essentially done, right? Because this is a short array, so it must surely work. But let me do it just by hand anyway. So here the smallest one, if you look at it, is going to be the 7. So I'm going to leave the 3 alone. I'm going to swap the 7 and the 13 and leave the other ones alone. So now the first 2 are sorted, and I'll do it again with the last 3. So now in this case the 9 will be the smallest, so the 3 and 7 are unchanged. I swap the 9 and the 11. So I always swap into the first one, and then 13. Now I only have to do these 2. So I'll do it one more time. Now the smallest one is the 11. So I'd swap it with itself, and then I'm done. The largest one must always be in place. So that's selection sort. That's all there is to it. And so it's an algorithm that you could have come up with if I asked you, tell me how you sort an array, because it's pretty intuitive, right? You say, in order to sort an array, I must know what is the smallest element. So let me find the smallest element. I must bring it to the front. And what am I going to do with that element that I'm now displacing at the front? I could stick it in the back, or I could just swap it with the one that I had. The advantage of swapping in place is it's cheaper. When you have an array and you want to stick something in the back or you want to remove something, you have to shift a bunch of elements. The swapping avoids the cost of the shift. So how good is it? One way to find out how good an algorithm is to just try it out on a bunch of inputs of different size. So here I did that using an array of 10,000, 20,000, 30,000, and so on elements, and I just ran how fast it was. This was a few years ago on a somewhat older machine. And so as it happened, to sort, to pick a data point here, to sort 50,000 records in this way took like 13 seconds. And so it was something that I was able to actually time with a stopwatch. Now you might say 50,000 records. That's a lot of records. When is the last time you had to sort any data that was that large? But think about it the other way around. Google would laugh at 50,000 records, right? Google has in its systems millions and millions and millions of web pages, and so when it wants to find something, it has to go through much more information than that. So for someone like Google, it makes a great amount of sense to study how fast or how slow a particular algorithm is. Now, all right, so we have this data, and now when we look at it, I've plotted it here. I was supposed to have plotted it here. Oh, I see what happened. I'll just draw you the plot since it's obviously not showing up. So when you plot the numbers, they kind of look like this. So n goes this way and the time goes this way. And what's remarkable about that is that it goes up more than linear. So if you double the size of the data set, the time that's needed more than doubles. So if we look at the numbers again, compare, for example, 10,000 to 20,000. So 10,000 to 20,000 went from 0.7 seconds to 2.1. That looks like it kind of tripled. But then look at 20,000 to 40,000. So here it looks like it went up by a factor of, maybe more than 4. Or from 30,000 to 60,000 also looks up like about a factor of 4. And that, in fact, turns out to be true for this data set. Generally, when you double the size of the input, then the running time goes up about 4 times. So let's see that you can do the math. I'll put this in Piazza. How did I label my options? A, B, C, D, okay. Question? Ja, spiace. All right, well, let's see if I manage to trick everyone here. So where is it? Where is it? Come on. So the rule was that if you double the input size, the time goes up by about 4. So here we have 100,000 data items. So let's look for a data point that's half of that. That would be the data point over here. So 50,000 takes 13 seconds. And so from 50,000 to 100,000, that's times 2. And from 13 seconds to whatever, then that would have to be times 4. So what's 13 times 4? That would then be the 53 seconds. So that's just the way it is. Let's see, people did. Yes, and so that's in fact what most people said. I'm going to have to find a way of limiting this thing to 5 minutes. All right, so so that's how it goes. So and 53 seconds is of course not that much, but if you double it again to 200,000, then you're almost talking 4 minutes. You double it to 400,000, now you're talking 16 minutes. 16 minutes is actual time. You would not want to sit in front of Google to put in a query and wait for 16 minutes for the answer, right? So in an interactive system, that would not be so great. As it turns out, we can do much better than that, and we'll see that on Tuesday. So first of all, let's now go through a systematic analysis as to what this algorithm does, where does it spend its time. And so when you make this kind of analysis, you have to find out some way, some currency that you can use to measure. So of course, the code is going to do a whole bunch of instructions, machine instructions. But you don't really want to analyze it at that level because it turns out it's just tedious to do, and you would need to know exactly what those instructions are. And there's an easier way. Instead, a pretty good currency that gives an approximation of the effort is if you simply look in the situation of an array, you look at every visit of an element, you charge $1, say. And now you ask yourself, how many dollars does it cost to sort 100,000? Well, it's got to cost at least $100,000 because you have to look at every element at least once to sort. But as you'll see, it's going to be quite a bit more costly than that. So our currency that we're going to be doing the calculation in is the number of visits of an array. So whenever the code says AI equals, that costs $1, and we're just going to count it as 1. If it says AI equals AJ, $2, please. If it says for I goes from 0, I less than n, I plus plus, look at AI, do something with it, that'll be n dollars. If n is 100,000, then that would be $100,000. If n is 200,000, it would be 200,000. Because each time there's n times that we traverse the loop, each time we charge that $1. So that's how one does this. So how do we find the smallest element in an array? So we have an array of numbers with n slots. To find the smallest element, remember how it goes. We say, oh, the first one is the smallest. Hope springs eternal. That was $1, please. Now we go through the remaining n minus 1 elements. We look at each of them, and we check whether it's actually smaller. Now, we pay per visit. So each time that we retrieve the element, that's $1. And then for the other stuff, for the comparison and stuff, we say, oh, that's not so important. That's just going to go under. It's proportional to that $1. So how many, what's our bill total? It's $1 for the first one, n minus $1 for all the others, or a total of n dollars. So that gives us the smallest element. But of course now we still need to do the swap. So we found the smallest element, say here. And then we need to do the swap. That'll be another $2. So the total cost is n plus $2. So that was to find the smallest element in the entire array. Now we do it again for an array that was one element smaller. So that'll be n minus 1 plus $2, because we're no longer looking at the initial element. And then we do n minus 2 plus $2, and eventually we'll look at the two last elements and a swap. So the total cost is n plus 2, that was the first one. I'm sorry, come on. N minus 1 plus 2, n minus 2 plus 2, and finally we have a 2 plus 2. Now, this can be simplified to... All right, so we're going to have to relive some math here to see how to do that. First of all, notice that the sum, that I have a whole bunch of 2's here. So I have, I'll sort those out first. 2 plus 2 plus 2. And then afterwards, I'll group the n plus n minus 1 plus n minus 2 plus 2. So that's the first terms here. Now, you'll recall that the sum of the, let me not use the sum notation as to not be hostile. So 1 plus 2 plus and so on plus n is n times n plus 1 over 2. So I almost have this thing here, except that I'm missing a 1. So I'll put it in and take it out. Then what do I have? Then I have, it's a bunch of 2's, and I don't quite know how many. I'll figure that out in a minute. Plus n plus 1 over 2 minus 1. So how many 2's do I have? Oh, I either have n or I have n minus 1. I have n minus 1. N minus 1. So that is 2n minus 2 plus n squared over 2 minus n over 2 minus 1. And so that is n squared over 2, which I have here, 2n plus, oh, let this not be a minus, that's a plus. Okay, good. Plus n over 2, that's 5n over 2, minus 1 is minus 3. Okay, so I actually did the computation right. All right, so the total number of visits is this n squared, whatever. Now, it turns out that I don't actually care whether it's n squared over 2 plus 5n over 2. What I care is this n squared. Because if you think about it, that explains why when I doubled the size, that it multiplied the time by 4. So let me show you that computation. And then I will go to what we can ignore. So what I was interested in is that I wanted to see what happens when I double the input. What's my effect on the time? So I took the original time, which was whatever it was, and then I divide those two. And now the squares are going to win out in this calculation. So let's just get rid of all of the junk, everything outside the n squared. 2n squared over n squared. The 2 sits inside here, gets squared. That gives you the 4. And you see that the n squares cancel out here. And so that's how I get that doubling the input quadruples the time. And that's the only thing I'm interested in. I'm not interested in knowing exactly what the time is. I'm just interested by how much it grows. And because after all, the whole thing was an approximation in the first place, I arbitrarily said I'm going to be looking at visits and not at every single operation. And so when you do these kinds of computations, what you're after is, does it grow linear, like this? Oops, like this. Does it go quadratic, or does it go even much faster than that? It's that, or maybe slower. Some of them go like that. So it's the growth behavior, and for that the rule is very simple. You figure out what the growth is, and then you only look at the most important term. So over here, we're only going to be looking at the square. So this stuff is a linear term. We don't care about it. This is a constant term. We really don't care about it. So here's this. And the other thing is, we don't care about the factor. We don't care that it's n squared over 2. Because when you do this computation where you check by how much does it grow when I double the input, whatever factor is here is going to cancel out anyway. So we don't care if it's 10n squared or 20n squared or n squared over 2 or n squared over 100. The fact that it's n squared that's what we care. And so the mathematical notation for this is what's called the big O notation. Does anyone know why it's called the big O notation? Because you write a big O. Trivia fact of the day. So I have no idea why it's called the big O notation, but you do write a big O. And inside that, you put the term that's the most important term. That's the term that grows fastest. When you have a polynomial, then it's always the term with the highest power. Later on, we're going to see some other things where we have logarithms and exponentials. Then we have to think harder what to keep and what to drop. But right now, for polynomial growth, you look at the highest power, you throw away everything else. So what we say is that selection sort is an O of n squared algorithm. And so the n squared says when you double the input, then you quadruple the time. When you triple the input, then the time goes up by a factor of 9, and so on. Yeah, excellent. After, I see. All right, before I look, let's see. So we need to find out how many more times is a million than 10,000. So what is a million divided by 10,000? So that's a lot, right? Unfortunately, we don't have a choice for a lot, so we have to figure it out. So these cancel. This one cancels. So it's 100 times as much. So the input size goes up by 100. And then the time goes up by 100 squared, which is what? That's 10,000, right? So I remember that to sort 10,000 element was was about a second. Let's say it's a second. So that means to sort a million is 10,000 seconds. Well, how much is 10,000 seconds? I have no idea. Someone says 3 hours. Let's see, 10,000 seconds is 166 minutes. Yeah, 3 hours. I buy that. All right. So it takes, just about 3 hours. Now that's actual time, right? In a million inputs, that's not that much. I mean, a telephone book is going to have a million entries. And so this doesn't look like it's the greatest sorting algorithm, and in fact, as it turns out, we can do better. All right. Now, one of the huge misconceptions that I always see beginning students run into, and I want to dispel that from the outset, is you guys will at some point feel compelled to memorize that selection sort is O of n squared. Merge sort, which we'll see next Tuesday, is O of n log n. And people always think that big O is for sorting, but that's actually not true. Big O is for any kind of algorithm where you want to know approximately how much does the time grow if the input size grows. So I'll be sprinkling in over the next few weeks a whole bunch of different big O exercises for different kinds of algorithms so that you get used to it. So it's a very important technique, and it's not just for sorting. So first of all, let's do a big O for something much simpler. What is the big O efficiency for finding the maximum in an array, for finding the largest number? And so here's how you approach it. You remember how the algorithm goes, and we've done it for smallest. It's really the same thing. So you say, oh, this one here was the largest one, and that's one visit. Then you look at the next one, maybe that one was the largest one, and so that's another visit. Then you look at the next one, and so on. So you have to look at all of the elements. If the array length is n, then that's an O of n algorithm. So anytime that you look at every element once, it's an O of n algorithm. What if you looked at every element twice? Then it would still be an O of n algorithm, because then the number of visits is 2n, but the constant factor, the factor of the coefficient doesn't matter. So anytime that you look at an element once or twice or three times, it's an O of n algorithm. So let's look at a more difficult algorithm. Suppose you want to find the most frequent element. So you have an array, and you want to look at which element occurs the most often. So here's an example. The array has 8, 7, 7, 5, and 7. Well, 7 is the most frequent. And that's easy to look at, but what if there's thousands of values? So what if that array goes on for thousands more values? How do you find the most frequent element? So you want to find the number that occurs more often than any of the other numbers. So here's an algorithm that'll work. So I look at the first element, the 8, and I count how often does the 8 occur. How do I find that out? I just go through the entire array, and every time I find an 8, I increment a counter. And then I store it away somewhere. Then I look at the 7, and I count how often does the 7 occur. And then I see another 7, and I'll just stupidly count again. Then I'll count the 5, and eventually for every entry in the array, I know how often this number occurred. And at this point, I have a second array of counts that says the 8 occurred 1,530 times, the 7 occurred 2,911 times, and so on. And then I go through that array of counts, and I find the maximum, which I already know how to do, and I know how long that takes. So, let's see how that goes. Each count is O of n. So to find how many 8s there are in an array of n entries takes O of n. In fact, it takes n visits. You have to visit each element once. And if it's an 8, you increment some counter. If it's not an 8, you don't. So you make one linear sweep for the 8. Now there are n elements. I make n visits for the 8. I make n visits for the 7. I make n visits for the next 7. So you have for n visits for the 8, n visits for the 7, n visits for the next 7, we're just being stupid, n visits for the 5, and so on. How many elements are there? There are n elements, so the total number of visits is n squared. And now we need to find the largest count. So somewhere we've now deposited in a parallel array here with the various counts. What did it say? 1530, 2761. This one would also be 2761. 9. Say this. Not very many 5s. An unpopular number. Now I need to go through this array here and find the maximum. That's O of n again, as we've seen on the previous slide. So altogether, we have O of n squared to establish the counts, O of n to find the largest one. Now, that's just when you do n squared plus n, you don't care about the plus n because it's dominated by the n squared. And so we'll say this is also an O of n squared algorithm. So you might say, so what? Well, the trouble with O of n squared is doubling the size of the input quadruples the size of the output. And so it's a little worrisome that something this simple, finding the most frequent element, can take potentially long. And so a computer scientist who looks at this, we don't really like O of n squared if it can be avoided. And so the question is there a better way? So let me ask that. Is there a better way? So the trouble with finding the most frequent number was that the numbers were all sprinkled all over the array. When I saw a bunch of 7s, I didn't know where the other 7s might be. They could be anywhere in the array, and I had to search the entire array for them. Just for the 7th, that was n steps. But let's say that the elements were already sorted. So if my elements look like this, and now I need to find the most frequent one. This is actually a lot simpler. And here's how I do it. I keep a counter of the longest sequence that I've seen so far. Now I see 3 4s in a row. I've never seen anything this long, so I remember, the 4, there were 3 of them. Then I move right on and say the 5, there's only 1 of them, and so then I'm going to forget about that. The 7, again, it's not exciting, it's no longer, but the 8, there's 6 of them. So I remember that the longest sequence I've seen is 6 8s in a row. Now to do that algorithm, notice that I only make a single pass through the array. I can look at this one, this one, this one, this one, this one, this one, and as I look at every one of them, I can update my information. Because here's what I do. When I see one that equals its predecessor, I increment the current counter. When I see that one that's different from its predecessor, I say, my run is over. Let's see whether it was longer than the previous one. So I can do that in a linear pass through the array. Hey, that's great. That's just O of n. So it looks like sorting might pay off. First sort, then just look at those sequences. All right, well, does it? So that's my last clicker question for the day. What is the efficiency of this combination? I never looked at the result here. I'll do that in a minute. Now we have a tile. This is great. I'm holding on for 75. And one more. Okay. All right, so let's see whether we still have a split vote. And interestingly enough, we do. Oh, this is great. So almost half said it's O of n. And half said it's O of n squared. So let's see what it is. We first need to sort with selection sort. And you have to pay for it. It's not free. Selection sort costs real money. Namely, it costs n squared dollars. So that's for the sorting. And then the second phase, where we find the most frequent one, well, that costs us O of n. So when you add them up, so this is the find most frequent. It's not only O of n because they're next to each other, but the sorting, we had to pay for it. It's not cost-free. So what's the sum of those two? Well, it's O of n squared plus n. So it looks like 2 would be the right answer. But remember, when you have a sum, then you can drop all but the highest term. So you get to drop this thing here. And so that's the answer. It is O of n squared. And of course, the bulk of the cost is in the sorting. So it does not look like the sorting was necessarily a better deal. That we had an O of n squared algorithm before, we have an O of n squared algorithm by doing it this way, and it doesn't look like one of them is dramatically better than the other. But as we'll see on Tuesday, there is a better and cheaper way to sort. And that will in fact make this scheme much better than the one that I outlined. There was a question?
Can you show us an example of a function that uses figure of
I'm sorry?
Can you show us an example of n cubed?
I'm sure I can, but not off the top of my head. I mean, in theory, you get an O of n cubed when you have to do an O of n squared thing n times. I'll give you a dumb example. Let's say that you don't just want to find the most frequent one, but you want to find the most frequent one, and then the second most frequent one, and then the third most frequent one, and you just do it in the silly way of running the algorithm, then running the algorithm again for one less and one less. That would be an O of n cubed algorithm. They're kind of rare because you don't normally have that much iteration. You kind of have to have like 3 nested loops to achieve that. But they definitely do exist in more sophisticated scenarios. All right, so just as a quick introduction to Big O. Big O takes a few days to sink in, and so I'll be putting in more of these Big O exercises. It's just the intuition that you need to have is when you have an array, going over it once, n dollars, O of n. Going over it twice, it's still n dollars. But 2 loops where you go over it n times, that's O of n squared. So that's all that I want you to get today, and we'll build this thing up gradually so that you'll be comfortable with it. So it looks like math, but it's actually nowhere near as scary. All right, so let's see if I had more questions here. So someone says, what does this mean, like in absolute terms? So first of all, let me say something. Notice that none of the things that we've been talking about, we didn't talk about, is the machine slow or fast? And when you do this, this growth analysis, you don't particularly care how fast the machine is. All that you care is what happens when you double or triple the data set. So on a slow machine, it starts out slow, and then it'll be 4 times as slow, say. On a fast machine, it starts out not quite so slow, but then it'll be 4 times the time still. So we don't particularly care when we do the Big O analysis. Still, so the question is, what makes a machine faster? And I'm, of course, the wrong person to ask because it's hardware, and I don't really know. But in a nutshell, the things that make the machine faster is the length that the signals have to travel. So if your chips are smaller, then it's faster. The clock speed that it can run at, and at some point, we're now at the point where if one could make the machines run faster. So you could take the clock and crank it up. And in fact, some people know how to do this. Some who like to tinker with their machines, they'll know how to change that circuit and make it run faster. But what happens when you do that on you buy the computer off Fry's, and now you double the clock speed? It'll work, but not for a very long time because it'll generate so much heat that the processor melts. So a big issue with that limits clock speed is the amount of heat that gets generated. And the other thing is, can you move the parts closer together? That gets harder and harder because there are only a few atoms thick these days, and you can't be less than an atom thick. So right now we're at this interesting space in time where the processors do not actually get much faster. When I had my first computer, I kept it for like a year and a half, and I threw it out and bought a new one because the new one was so much faster. That was just a no-brainer. Yeah, I wasted $3,000, but if you're in the business and you can work 4 times as fast, that's easily worth it. And for several years, for like a dozen years or so, every year and a half, I would go and throw away my old, first was a desktop and then a laptop and a snazzier laptop. After a year and a half or so, I would throw them away. And I would tell my wife, hey, it's so much faster. It's well worth the money. Don't worry. Now I still try that, but it doesn't really work anymore because when I get the shiny new laptop, it's not 4 times as fast. It's maybe itty-bitty little more faster, mostly because there's not so much to gunk it up yet, but it's not actually really going any faster because they don't know how to make them any faster. Instead, what they do, they give me more processors. So now I have 4 processors. I'm sure the next laptop that I buy is going to come with 16 or some such thing. I have no idea how to keep them busy. I only have one brain. And that is a big challenge of computer science right now. How does one get people like you and me to write programs that keep all of these cores busy? And that's not something we can do in CS1 and CS2, but at some point in your undergraduate curriculum, make sure to take a course that teaches you techniques on how to deal with that, because programmers who know that are going to be in great demand. So, nested loops. Is there a relationship between nested loops and Big O? And absolutely yes. So when you have a loop that makes n iterations, nested inside another loop that makes n iterations, that gives you n squared iterations. If you have a loop inside a loop inside a loop, that would give you n cubed iterations. So that is absolutely the right way of thinking about it. And when the loops are directly nested in each other, you can really see it. But so oftentimes what happens is we structure the program to make them easier to read so that one loop calls a method, and that method contains the other loop, so you kind of have to disentangle that in your mind. Or you have to just charge more for the method call. All right, looks like that's taken care of those. No, here was an unresolved follow-up. Let me try to get that. And so here someone asked, are we using selection sort as a part of it? And yes, you must, because if you say we're going to be using selection sort as the first step, there's no free lunch. You've got to pay for it. All right, on to the lab. So I decided to make a lab that touches upon a few of the issues where people had a harder time than I imagined on the exam. So the first exam question here, because so many people had trouble with this, I want to spend a minute to go over with this. And I wish I could take credit for having invented this question, and I didn't. A colleague of mine did, but I thought it was such a beautiful question that I just had to put it on. And so let's see what happens here. So they asked, the question asked, which exception can this throw? And it limited to 2 exceptions so that no one could think of some other things like out of memory exception or something. It said, can this thing throw a null pointer exception? Can this thing throw an array index out of bounds exception, out of the method? And it gave the hint. Only one of them can happen. Now let's see. So we have the entire body of this method, except for this thing which clearly can't throw any exception, is surrounded in a try-catch block. And in the catch block here, it doesn't throw any exception either. So let's say, for whatever reason, this thing throws an array index out of bounds exception. What happens? It gets caught right here. It gets eaten up, and something returns. So some last values cannot. It simply cannot throw an array index out of bounds exception because the method itself catches that exception. So the reason that people had such a hard time with it, I think, is that they say, well, how could it throw a null pointer exception? Right? There's nothing null in here. You know, A is an array. It's an array of integers. Integers can't be null. And so obviously it can't throw a null pointer exception, so then it must throw an array. So somehow people got themselves, I think, entangled into that knot. And so I realized that's because people are not so sure whether an array can be null. So I want you to study this. Part B. I know it's difficult to trace a recursion, and it's no one's idea of a good time, but it is an essential skill. There were a whole bunch of people who were unable to do the problem on the exam, or maybe who didn't attempt it on the theory that it takes some amount of time. And so I just want to have some more practice with that. And so I'm doing again the thing that, so first of all, if you did the exam prep, which I think in hindsight seems like a good idea, and if you did the substring generator from the exam prep, pick your own substring generator, the one that you or your buddy programmed, and run through a recursive call that finds the substrings of Fred, do the index cards business, and run that. If you didn't do this, you could discuss with your buddy whether you now regretted that decision, then trace through the solution of homework 4, just like on that last question of the exam prep. Do it by hand with pencil and paper. So get out your pencil and papers, make some index cards, or simulate the index cards by drawing on the sheet of paper. If you're not clear about how the format works, look at the solution to the exam, and there you see the general format, and just imitate that. So I really want to see that. I'll take those home and study those and see what you guys are writing on those. And then part C, the reading code part. So there was a question in the exam. It was the last question. Not everyone got to it, and that's understandable. But the reason I put it on there is I want to emphasize the importance of reading code. And so let me pull up this code real quick here. Goodness, which one was? Does anyone remember which assignment this was? Okay, 3B. So it was this code where we're reading these kinds of options. And now, of course, you don't really remember all the problem, but when that solution came out, what I really want you to be in the habit of is to download my solutions and read them. And when I say read them, I mean not just look at them and say, oh yeah, that looks interesting, but to actually try to find out what did I do that is different from what you may have done. And in this particular problem, there were so many different ways of doing it that I'm pretty sure that what I did was somewhat different from what just about everyone else did. And so in particular, what I want you to pay attention to in this lab is how does the question text get accumulated? So here it starts out in a certain way, and then here the stuff gets added to it. And so I want you to actually understand that. And I want you to get in the habit by the time that the semester is over that you can look at a solution and you can spend 15, 20 minutes with it, tracing it through in your mind or with a sheet of paper, and that you can kind of read it like you would read a bit of English. And it takes a lot of practice to do that. And so I'm handing out these solutions, and I'm handing them out as quickly as possible after the submission deadline so that you really do this. And my expectation is that you do download my solutions and look at them from the point of view, what did I do that would have been a good idea for you to do? And so in the next exam again, I will ask a question that say, do something with this solution, carry it to the next step, improve it or something to make sure that you do this. It's very, very important to be able to read code. One of the most common complaints that we get from employers is these people know how to write bad code, but they don't know how to read bad code. And so it really is a very important skill. And it's something that takes a lot of practice to go from becoming a beginner to becoming an expert, and you have to start somewhere. And so what I realized when I was doing the grading is that when I graded the written answers, the word answers, I pretty much had to read through what you were writing. But when I was looking at the code, in almost all cases, I was able to glance at the screen for less than a second. And because I've seen so much code in my life, I was able to see, is the algorithm basically is it basically right or is it basically wrong? Then you still have to look at the details. And so I was actually kind of surprised at this, but there's research that shows how experts in other fields, how they can quickly absorb information. Chess players, for example, if you flash a position of chess pieces for a fraction of a second on a computer screen or on any kind of screen, and you ask a chess player versus someone who doesn't play chess like me to reconstruct the position, with a bunch of chess pieces. The expert chess player can do this. They look at this thing, it's there for a fraction of a second, and they can reconstruct it, provided it was a real chess position. If it was random pieces, they can't do any better than you or I. So in the brains of the chess players, as they have looked at more and more things over time, they get to have expert knowledge about where stuff is kind of supposed to be, and they can deal with this very quickly. And so the professional programmers are the same way, and so the way you get that is by reading code. By writing code, of course, but also by reading code. And so it really is an important and is an essential skill. You should not expect to get to to this level of mastery by the end of the semester. So I'm not going to flash code for a fraction of a second to you at the end of the semester, but still, it is something that people over time can get quite good at, and so you've got to start somewhere. So let's get going with the labs, same buddies, same everything. I'm going to make one final pass at the buddy list next week, but today we're going to still have the same setup. All right.